So for number 45, I want to see if the sequence over here, if it converges. And now a sequence an converges if an, it tends to a specific number, the limit, as n approaches infinity. So we're going to take the limit as n approaches infinity of our an of n sine of 1 over n and see if this spits out a particular number. So let's see what this looks like. The limit as n approaches infinity of 1 over n, this is like 1 divided by an infinitely large number, so that's going to be equal to 0. And so over here we have, let's see, infinity as n goes to infinity, so that's infinity times sine of 1 over n. That's going to give us, as we saw previously, 0, so sine of 0, and that is going to be infinity times 0. And now we don't know what this is, right? We don't know whether infinity wins, whether 0 wins. This is weird, this is indeterminate, and the tools that we have to deal with indeterminate form, the tool is called L'Hopital's, but this is not in L'Hopital form. L'Hopital needs to be either infinity over infinity or 0 over 0 for it to work, not infinity times 0. So what we're going to do here is we're going to just change things around so that we can express this in L'Hopital form. So I'm going to say that this is the limit as n approaches infinity of sine of 1 over n divided by 1 over n. So the sine stays where it was, and the n I divided by 1 over n. So this ends up being the same thing, right? Because if you divide by division, it's like you're multiplying. And now when I take this limit, I'm going to get sine of 1 over n, that's sine of 1 over infinity. So sine of 0, that's 0, divided by that's going to be 1 over infinity, which is 0. So 0 over 0, hey, this works. That fits in our L'Hopital form. And so if you remember from the discussion of, actually I should leave this here. If you remember from the discussion of L'Hopital as it pertains to sequences, we use L'Hopital when we deal with a function, right? So maybe let's take this function. Let's suppose we have a sequence 1 over n, and then we're approximating using the function 1 over x. So that's going to be, so this is going to be our function 1 over x in blue. And it's all these points that are continuous. So this is 1 over x. However, our 1 over n are just going to be the discrete points at all the natural numbers. So at n equals 1, n equals 2, n equals 3, and so on. So we can see that it begins being defined at n is equal to 1, and then it goes at 2, 3, 4, just at discrete intervals. However, we can see here that both the sequence and the function, they're heading to the same place, right? Because they're essentially the same thing. The only difference is that the function is continuous and the sequence is discrete, evaluated at the natural numbers. So what we're going to do here is, since we know that the function and the sequence described by the same equation, they head to the same place, we're going to approximate using, we're just going to turn this, the limit as x approaches infinity of sine of 1 over x divided by 1 over x. So we just turn this into a function of x, because now we can use L'Hopital, right? We can use L'Hopital. So to use L'Hopital, we're going to first differentiate the stuff that's on the top and then the stuff that's on the bottom. So the derivative of sine of 1 over x, that is going to be cosine of 1 over x times the derivative of the inside. So the derivative of the inside is times negative 1 over x squared. And then on the bottom, we're going to have the derivative of 1 over x is just negative 1 over x squared. And so these cancel. Then we're taking this limit as x approaches infinity. And then we can see here that these cancel out. So all we're doing here is we're taking the limit as x approaches infinity of cosine of 1 over x. And this limit here, it's like saying, okay, cosine of 1 divided by a very large number. So that is equal to cosine of, actually, let me make this a little bit better. 1 divided by a very large number is 0, right? So that's cosine of 0, and cosine of 0 is equal to 1. So we can see that we've taken this limit using the function that gives us 1, right? So we can say that using L'Hopital, the limit as n approaches infinity of sine 1 over n divided by 1 over n is equal to 1, because as we've seen, the function and the sequence, they go to the same place. And so because this limit exists, we can say an tends to 1 as n tends to infinity, right? We're saying, hey, this limit is 1 as n gets larger and larger, so an converges. So it converges, yeah. And so if we just backtrack, we turn this into L'Hopital form, and then we took the derivative on top and on the bottom, right? That's cosine of 1 over x times negative 1 over x squared over negative 1 over x squared. These cancel out. We're just left with limit of cosine of 1 over x, that's cosine of 0 is equal to 1. And so the limit of this whole thing is 1, and the sequence converges.